So far we've been using rectangles to get an estimate for the area under a curve over some interval. And if we use big bulky rectangles, the advantage is that you only have to find the area of maybe one or two rectangles, right? A quicker calculation. What's the disadvantage of using a few rectangles? Good. Yes. Your estimate is going to be less accurate. Conversely, if you use a whole bunch of rectangles, you can make them nice and skinny and fill in a lot of the space, and then you'll get a more accurate estimate. Of course, the downside to that would be
Takes a long time.
Takes a long time, yeah. You want to use 62 rectangles? Good for you, kid. See you in a couple hours, right? So today, we're going to actually find, in the end of the exciting conclusion of section 4.2, we're going to find exact values under a curve by using so many rectangles you can't even count them. Infinite rectangles. More rectangles equals better area estimate. Therefore, an exact area comes from infinite rectangles. Sounds like the name of a pop punk band. Ladies and gentlemen, all the way from Toma, Wisconsin, infinite rectangles. They'd be covering the Ramones, probably. No? Never mind. So that's what we're going to be doing today. We're going to be using infinite rectangles to get exact values for areas under curves over some interval. Kind of a quick review here. The width of a rectangle in these estimates. To get the width of any one rectangle, what do you have to do? Perfect. Yeah. Figure out how wide your interval is. So take your right endpoint minus your left endpoint. That'll tell you how wide the interval is, right? Divide that by n, which is the number of rectangles that you're using to get your estimate.
Is it an infinity?
It's going to be today.
So we're going to do a limit.
Exactly. Yeah, we can't actually plug infinity in. I mean, you kind of can, hypothetically. It's not really a number. It's more of a state of mind. So to get by that, we're going to say not really n is infinity. We're going to say the limit as n approaches infinity. Kind of like we did for the limit definition of a derivative. And so these problems, much like the limit definition of a derivative, these are going to be long algebraic problems. And then we'll talk about a shortcut way of doing it after we get the long cut down. So the formula for exact area then. What we're going to do is we're going to take the limit as n approaches infinity of a summation. The summation is going to be exactly what we've been doing with our finite number of rectangles. By putting limit as n approaches infinity in front of it, we're saying, all right, now make our finite estimate an infinite estimate, an infinite rectangle estimate. Inside the sigma, there it is. Wow. Inside sigma, we'd have the heights of the rectangles, right? And we get the heights by using the function. Plugging numbers into the function tells us the height of each rectangle. If you're using left endpoint rectangles, what's the very first number you want to plug in?
0.
Well, if you're starting, if your interval starts at 0, you plug in left.
F of A.
Good. In general, you want to put in the left endpoint, which we call A, right? So A is going to be the first thing you plug in. That'll give you the height of the leftmost rectangle. And then each subsequent rectangle is how far down the road. However wide they are, right? However wide the rectangle is, that's how much further you want to go down the x-axis to plug in the next number. There you go. B minus A over n will be the next rectangle. And the next rectangle over that would be another B minus A over n down the road. Because this is the width of a rectangle. So by adding on widths of a rectangle, you are finding all the x values that you want to evaluate. So in short, what do we want after the B minus A over n? What's that? Not quite what I was going for. We want to stop when we get to f of b, but we'll do that automatically if we keep adding these things on, right? Do you remember on the worksheet 4.2 that you had where you had to write a sigma notation for finding area using finite rectangles? In your sigma notation, you probably had f of some number plus a fraction. Yeah, and then you had to tack an I on after it, right? And this I means keep adding these widths on time and time and time again.
I approaches B.
That's one way of looking at it, yeah. Since we got it set up in terms of n, though, I'm going to write it a little differently. But you're right. When I and b are the same, you'd stop. Or when, well, when I guess all this equals b, you'd stop. But in short, I'm going to start with I equals 1, because that way we can use our shortcut formulas. Because all those shortcut formulas, remember, are set up for I equals 1. And we're going to stop when we get to n, which is infinity, essentially. So we're not going to do this manually. We're going to look for the algebra to do it for us. I'm also leaving off the width. Normally we'd have, I think on 4.2 we were generally putting the width out front because it was a constant. So whether you put it out front or inside doesn't make a difference. Since I didn't put it out front, I better put it inside. So we're going to multiply that by the width of a rectangle, which we've already said is just b minus a over n. This has a name. This is a sum, because you're adding up a bunch of things. And assuming the mathematician came up with this concept, it's named after him. It's called a Riemann sum. So if you ever say, find the Riemann sum that gives you the area, they mean, write this out. That's what they're referring to. By they, I mean me or book or the AP test, whatever. Whatever you're doing. So this much gives you the height of a rectangle, and this much gives you the width. Multiplying the height and the width gives you the area, which is what you're trying to find. Adding up a whole bunch of them gives you the area of an entire region. How are we doing? All right, so example time.